Welcome back, students. We now are taking a turn from describing thermodynamics using the bulk properties of systems, as we've been doing in the first part of this course, to looking at the microscopic properties of the system. We will see that the bulk properties that we've been talking about, enthalpy, entropy, heat capacity, Gibbs free energy, and so forth, can be explained and described by considering the energetics of the individual molecules that make up the system. And by the energetics, I mean things like vibrational degrees of freedom, rotational degrees of freedom, etc. The key to doing this is recognizing that we can describe all of the molecules in the system without directly considering them. Instead, what we're going to do is use probability theory to determine what the average molecule is doing. And since any molecular system uses a large number of molecules, the average result becomes the only result possible. We'll continue discussing this idea in the future, and this is first recognized by Boltzmann, where you recognize the name from Boltzmann's distribution. We'll start today with an introduction to probability before attempting to apply it to molecular systems. So we'll be talking about basic probability theory today, mostly using things we're very familiar with: coin flips, decks of cards, die rolls, and the like. The learning goals for today are going to be to apply probability theory to describe simple games of chance, like I just mentioned. And then we're going to want to be able to also explain the connection between this very basic probability and chemistry. And we'll continue working on this point throughout the next couple of lectures. At the end, we'll apply Stirling's approximation, which will allow us to work with large numbers and determine the probability of very large numbers. All right, so probability theory was originally developed in the late 17th century as a way to describe games of chance. For example, we might want to know how likely we are to roll snake eyes or an 11 when we're playing a game of craps compared to a 7, where rolling 2 or 11 is good and a 7 is bad. And we can pretty easily calculate the probability of these sorts of things. So for snake eyes, there's only one way to roll snake eyes out of a total of 36 options with 2 dice. So that's a 2.8% chance. There's 2 ways to roll an 11, and we could get 5.6% chance, but there are a variety of ways to roll a 7 for a total of about 16% chance. So 6 out of the total 36 ways. Probability often comes in the form of discrete variables, and that's how we'll see it today. So a discrete variable is like I flipped 2 coins, or I rolled 3 dice, right? We have 2 and 3. We can't flip half a coin, so we have these discrete variables. Once the number of events becomes sufficiently large, so instead of flipping 2 coins or 10 coins, if I'm flipping 1,000,000 coins, it kind of can become annoying to use discrete variables. And we'll talk next time about how to convert these variables into continuous variables. The core concept of probability is that all probabilities must be between 0 and 1, as you see here. And then when you add them all together, they must be 1. Often we think of probabilities as being equal from games of chance in order for those games to be fair. That does not have to be the case. So if we're flipping a coin, we think that we have a 50% chance to be heads and a 50% chance to be tails, but you can have all sorts of probabilities that still make sense. If you had a weighted coin, you could have a 60% chance to get ahead and a 40% chance to be tails, and that's still fine. And we can still easily describe that with probability. All that has to be the case is that our probabilities are in between 0 and 1, and they all add up to 1. With probability, I think hopefully we've all played enough games to understand that if you have a small number of events, the probability appears random. So for example, if you roll a die 6 times, I think you would be shocked if you rolled a 1, then a 2, then a 3, then a 4, then a 5, then a 6. You would be surprised if you achieved that perfect result where you rolled every outcome exactly once. But when we get to large numbers, we have been told, or we have the expectation, that we should eventually yield these expected results. So if we rolled 6 dice, we might not get 1 of each. If we rolled 60, we probably wouldn't get 10 of each. But if we rolled 600,000, we should probably get pretty close to 100,000 of each option. And we'll look at that as well as the continuous variables in the next lecture. So today we'll focus on the basic sort of counting statistics that we could talk about. Now, why are we using probability in the first place? What does this have to do with chemistry? If we have a mole of molecules, that is a very large system. And if we describe the probability that a single molecule is going to do something, if we have Avogadro's number of them, that's all of a sudden a very, very large number. And we would expect that very large number of things to behave exactly as we would expect with probability theory. And we'll look at that as well in the coming lectures. So let's start by considering a pretty basic example. And we might want to know how many 5-card poker hands are there. So if we're dealing out a poker hand of 5 cards, how likely are you to get a certain hand? And to know how likely you are to get a certain hand, you need to know how many options there are. So what would happen? Well, if you have a 52-card deck, the first time you get dealt a card, you have 52 different options to choose from. You have 52 options for your first card. What about your second card? Well, now you don't have 52 options anymore. Now you have 51 options, and so on and so on. So if you were to talk about a 5-card hand, for your first card, there'd be 52 options, then 51, then 50, then 49, then 48. So those are all the options that you could get. You multiply those together for a total of 311,875,205 card poker hands. Note that this assumes there are 52 exclusive options. So if I draw the ace of spades for my first card, I can't also draw the ace of spades again for the second card. If we were to shuffle the original card back into the deck and draw a new one every time, it would just be 52 times 52 times 52 times 52 times 52, which would give us about 380 million options. So we'd have more options if we're not taking cards out of the deck, which seems pretty obvious. Some interesting facts about these poker cards here. For a 52-card deck, how many options are there for arranging that? Well, we would take out this same sort of path that we just did, but we would take it all the way down to 1. So to do that mathematically, we say that is 52 factorial. The factorial is whatever number it is multiplied by every single integer below it. So for a 52-card deck, there are 52 factorial arrangements, which is about 8 times 10 to the 67 arrangements of a 52-card poker deck. This number is so large that every time you shuffle the poker deck, you're more likely to shuffle the deck into a never-before-seen arrangement than one that has been shuffled before. So that's pretty fascinating to me. Each of these arrangements is called a permutation. And often when we're talking about permutations, we don't necessarily talk about the overall number of arrangements, but we care about a specific one. For example, what are the permutations involved with drawing 5 cards out of a poker deck? And we have an equation that we can use to calculate this instead of just multiplying all of these things together, although they end up being the same thing. We can say that the permutation is equal to n factorial, where n is equal to the total number of options that we have, and then over n minus j, where j is the number of things that we're looking at out of the greater set. So if we have a set of 52 cards, n is 52, and if we want to know 5-card hands, j is 5, and we take 52 factorial over 52 minus 5 factorial, which is 47 factorial. And if we look at this, this would be 52 times every number below it, divided by 47 times every number below it. So the 47 all the way down to the 1 are going to cancel out. And what we're left with is 52 times 51 times 50 times 49 times 48. So this is the same thing as we have up here, just a bit more concise. This permutation number is not yet the whole picture. So if we carefully consider what this permutation is doing, I don't actually have 311 million different poker hands. And that's because what this is saying is for my first card, I draw, I have 52 options. For my second one, I have 51. For my third one, 50, 49, 48. But it doesn't care if I draw cards in a different order. So for example, if I was dealt a hand and the hand was ace of spades, king of spades, queen of spades, jack of spades, 10 of spades, I would say I have a royal flush. And that would be one of these permutations. But it would actually be a different permutation if I was dealt the king of spades, the jack of spades, the queen of spades, the ace of spades, and the 10 of spades. Now that is still a royal flush, and I'm still pretty happy with being dealt that poker hand, but it counts as a different permutation because they come to me in a different order. What we're going to do next is try to figure out how we can get rid of this order parameter, because we often don't care about the order things are coming in. We just want to know, well, what are my options? And to do that, we're going to look at a little bit easier example to describe, and that is going to be flipping coins. And specifically, it's going to be flipping 4 coins because I can much more easily figure out the total number of options with 4 coin flips than with 52 cards in a deck. So we can describe 4 coin flips by the brute force method, by writing out how many options there are. And so if you would take a minute here to go ahead and write all of the possible options for flipping 4 coins in terms of heads and tails. All right, so hopefully you paused the video and wrote down all of those options. We can describe them pretty easily. So we could have one outcome in which we have all 4 heads. Then we can just simply swap out, one of these each for tails. So there are outcomes where one of our coins is tails. We have 4 outcomes that have 3 heads. We have 6 outcomes here that represent 2 heads. We then have 4 outcomes that are 1 head or 3 tails, and then 1 outcome that's 3 tails, for a total of 16 options. If you look here, the way we get 16 options besides just counting is that we have 2 outcomes, heads or tails, and we have 4 coins. So we raise 2 to the 4th power to get the total number of outcomes of 16. With that, we can divide all of these numbers by 16 to get their percent likelihood of being measured. So here we have 1 out of 16 ways to get 4 heads for 6.25%. Same with tails. We have a 25% chance, 4 out of 16 for either of these, and then we have a 37.5% chance to observe 2 heads. This goes along with our expectation that we're most likely to get an even number of heads and tails. However, if we plug this into the permutation equation, we get a weird answer. We get that permutation is 4 factorial over 2 factorial, which is equal to 12. Now, that's not very helpful here. And what is this 12 really telling us? Well, what this permutation is telling us is, again, it's taking the order into account. So we're asking, how likely am I to pull 2 heads out of a flip of 4 coins? And so what this is saying is I could take any one of these 6 options, but I could pull this heads first, or I could pull this heads first, and those would be different permutations. And of course, to us, that sounds weird, and I'm not really interested in that. Why would I care about that? But that's what this permutation equation is doing. So we need a correction to actually better account for this. And that correction that we're going to use is called the configuration. So we've already discussed this a little bit, why we get 12 when we only expect 6. Our permutation count here doubles each success because it says we can grab either this head first or this head first, where that kind of doesn't really make sense to us because we're not flipping individual coins. They're all kind of equal in our minds. So we can recognize with this simple situation that there are 2 ways we could grab head 1, then head 2, or head 2, then head 1. And so if we simply divide 12 by 2, we end up with 6, which is what we expect. Now, more generally, if we don't have 2 successes, there are j factorial ways to arrange something. So for example, if we were talking about the 3-head situation, there would be 6 different ways we could pull those 3 heads out of a bag, which would be 3 factorial. So our configuration is simply the permutations divided by j factorial. So if we take the configuration of our 4-2 situation here, where we have 4 options, and we want to know how likely we are to get 2 heads, we end up with 4 factorial over 2 factorial, 2 factorial, which is then 24 divided by 2 times 2, which is 24 divided by 4, which is 6, the number that we expect here. And if we plug this into all of our other options, we get the same thing. So how likely are we to get 4 heads? That would be 4 factorial over 0 factorial times 4 factorial. If you don't know this, for probability to make sense, 0 factorial is defined as 1. So that would give us 24 over 24 is 1. There's only 1 outcome, and we can do the same with the rest of our options here. If we go back to the deck of 50 cards and try to evaluate this, the configuration associated with a 5-card draw would be 52 factorial over 47 factorial times 5 factorial, where 5 factorial is 120. So for any given 5 cards, there are 120 different ways in which they could be dealt to you. So we divide by 120 to remove that. And there's only about 2.6 million different 5-card hands. So if you want to know how likely you are to get a royal flush, you can simply divide this 2.6-ish million. Take 4 divided by that, which will give you the number of outcomes. So you have a 0.000154% chance of being dealt a royal flush, which would be 1 out of every roughly 650,000 hands would be dealt a royal flush. I did some calculations, and if you're allowed to discard 3 cards, your odds increase from 0.000154 to 0.000186, so slightly higher if you can discard some of your cards. Here, I want to mention the binomial distribution, which is an equation that will allow us to determine how likely we are to see a given option. Now, the binomial distribution requires one thing that might seem kind of strict. It requires only 2 options to be observed. So we could use this to describe heads and tails. Now, this might seem restricted, but we can actually apply it pretty easily. So if we wanted to roll a die, we could consider rolling a 6 a success and rolling a 1 through 5 as a fail. And that would give us a binomial distribution where we have a success or a fail. We can also apply this to real chemical systems. So for example, we could apply this to some sort of DNA polymerase, where the success is incorporating the appropriate nucleotide and a fail is incorporating the incorrect nucleotide. So this has some wide application in games of chance and outside games of chance. The form of the binomial distribution can be seen here. So P is the probability of observing J successes with N total events. And that is equal to the configuration of N and J, which we've described before. That's multiplied by P raised to the J. So P is the probability of success and J is the number of successes. And then that's multiplied by 1 minus P, the probability of failing, raised to the N minus J, the number of fails. And we can see this equation here. It relies only on the number of successes, the total number of options, and then the probability of observing success and failure. So we can apply this to all sorts of situations. Going back to our coin flip, the likelihood of observing 4 or 2 heads out of 4 total flips is equal to the configuration, which was 4 factorial over 2 factorial times 2 factorial, which is 6. And then here, our probability of success is 0.5, and we want 2 of them. Our probability of failing is also 0.5, and we want 2 of them. So that gives us 6 out of 16, or 37.5%. And this equation is readily changeable if you wanted to do something like die rolls. So if you needed to roll 2 6s out of 4 dice, the configuration would be the same. The probability of success would now be 1/6, and the probability of failure would be 5/6. You get a much different probability. You'd be much less likely to succeed with 2 6s out of 4 dice. And you can calculate your probabilities, and this can maybe help you make some sense of some games of chance you might be playing. Lastly here, we'll discuss Stirling's approximation. So we can see, going back to the last slide, that often what we end up needing to describe probabilities is factorials, and that's fine. We can take factorials for numbers. Our calculators have a function for this. If you want to work with systems that are larger than a deck of cards, and for example, we're eventually going to want to apply this to Avogadro's number of molecules, we quickly hit a problem. So unless your graphing calculators are sufficiently better than mine, my calculator won't evaluate 70 factorial. 70 factorial is equal to 1.2 times 10 to the 100, which is greater than the number of units that our calculators have room for. So the calculator can't handle the large number and gives you an overflow error. If we use Microsoft Excel, it can do a little bit better. So Microsoft Excel can go up to 170, and it gives 170 factorial is 7.26 times 10 to the 306. But 171, it won't do. I'm not exactly sure why Excel runs out there. It seems kind of a weird number, but that's where it runs out. And nevertheless, we want to describe systems that are bigger than 170 particles. We eventually want to describe a system with Avogadro's number of particles. So what do we do? And what we'll do is we'll turn to Stirling's approximation. So I've shown Stirling's approximation here, and we'll mainly use it in this form over here. So Stirling's approximation is a way to measure n factorial. So the natural log of n factorial is approximately n natural log of n minus n, and then we can add 1/2 natural log of n plus 1/2 the natural log of 2 pi. When n gets sufficiently large, n natural log of n becomes much bigger than this, and we can approximate this out as well to get n natural log of n minus n. The book goes through a proof of this, and essentially the way that we can prove this is that the natural log of n factorial is equal to the sum of the natural log of n plus the natural log of n minus 1 plus the natural log of n all the way down to 1. And if you have a sum of a large number of things, that's approximately the integral of a large number of things. And then we end up with this expression here. Now, how does this actually work? Let's go ahead and look at some examples here. These are all the ones that Excel can actually do. So here I have the numbers, and then I have the natural log of n factorial as evaluated by Excel. Here we have n natural log of n minus n. And you can see that for these small numbers, it's kind of okay. So for 10, it's off by about 2, and then it's off by about 3 and 3 and 3 and 3. So it's about off by 3-ish. And it gets actually more off as n gets larger. If we incorporate this extra correction here, it's actually pretty darn good. So even for 10, our natural log of n factorial is 15.10, and this gives us, I guess 104, this gives us 15.096. So it's off by about 0.008, which is pretty close. So it's a pretty good approximation if we use these correction terms here for these small numbers. But after this, we run out of our ability to calculate these things. Now, I suppose we could, if we really wanted to, by hand, multiply 170 factorial that we can calculate by 171. That would be a pain in the butt, and I would not want to do it. So it turns out we can use this approximation instead. Let's look at the next section of our table here that gets into larger numbers. Here we see that our n natural log of n continues to increase as we expect. However, this 1/2 natural log of n it still is increasing, but it gets pretty small. So at the beginning, where our 1/2 natural log of n plus 1/2 natural log of 2 pi is 2 compared to 13, and 2 is a pretty sizable part of 13. For 50, we're at about 3, which is still a pretty sizable part of 146. When we're down here at like 1,000, we're now talking about 4 parts out of about 6,000. And that becomes pretty small, where we can start to ignore this extra correction term. Down here at 100,000, you can see we're at about 7 out of 1,000,000. And that's, again, pretty small. So lastly, we can apply this also not only to these large numbers, but to something like Avogadro's number. And you can see when we apply, this isn't quite Avogadro's number, this is just 10 to the 23, so 1/6 of a mole. Our n natural log of n is very large now, it's 5 times 10 to the 24, whereas our extra correction term is only 27. So we can pretty safely ignore 27 out of 5 times 10 to the 24. Now, how does this work, and how do we actually go back and get n factorial? What we're calculating with Stirling's approximation, when we do n natural log of n minus n, we're always getting the natural log of n factorial. So if we want to go back into n factorial, which we sometimes do, we simply have to raise e to whatever number we get. For example, here, 10 factorial, we can raise e to the 15.10441, and that will get us what 10 factorial should be. And that would be 3,628,800. For these other ones, it can get kind of hard to do, and we have a simple equation that we can use to get this. So instead of taking e raised to our n natural log of n minus n, we can do a change to base 10, which we're usually more comfortable in thinking about, and that is 10 raised to the 0.434 times n natural log of n minus n. So in this case, our n factorial for 10 is this number that we could actually calculate. For 50, it's about 3.04 times 10 to the 64, and then 9.3 times 10 to the 157, and we keep going up and up and up. So down here, we can use our approximations. So for 200, we can't actually measure it. So these are all measurable. We can't measure 200. We can't do this with Excel or our calculators, but we can use our n natural log of n minus n, multiply this number by 0.434, and say that this is approximately 10 to the 375. and then it keeps increasing. And if we wanted to go all the way down to, again, almost Avogadro's number, this is now 10 raised to the 2 raised to the 24. So an insanely large number. We have an insanely large number of possible outcomes for these systems. That's going to be it for today for this basic discussion of probability. In the next lecture, we're going to consider extrapolating our discrete variables to a continuous variable setup. So going from not 1, 2, 3, but we could have non-integer values, see how we do that. We'll talk about probability distribution functions, and all of this will prepare us to actually start applying probability to molecular systems that we'll do after spring break.